I want to start, so as you know, as part of the introduction, I come from the Santa Fe Institute, which is a place where for almost 30 years now, it'll be 30 years next year, we have been looking at complex systems. And in some sense, there's been an evolution as to how we look at complex systems, from building simple models that capture some of the basic dynamics of emergence, of nonlinearity, of chaos, to increasingly really turning that into a science and looking at lots of data and trying to build models that really bring fundamental concepts from many disciplines and really create new science. So hopefully what I'll be telling you about today is a little bit about how you do that for cities. How do you understand cities as complex systems, and specifically how do you go from understanding a little bit about people, not everything, but just a little bit, how we are social and how we are biological, and how these two things somehow create an interesting tension, but also an interesting set of new solutions that will argue actually are new in nature. So let's see if I succeed at doing that. So before I start, this is our group. There was a question before about how do we organize ourselves to be complex systems researchers and groups. We have people here from physics, from economics, from anthropology. Marcus, an anthropologist, from regional science, from mathematics, from geography. So that's how you do it. You find a group of people that you enjoy working with, hopefully young people full of energy, and you just basically try to ask some very interesting questions that you can solve by having data, by having some ideas about how to approach the problem, and by trying to create new theory that establishes those concepts. So that's more or less how we operate. If you have interest, ask me more. So you've seen this before, but this is basically looking from the space station at Earth. You know, for many centuries we've been looking at the sky and seeing galaxies and planets and stars in the sky. But the amazing thing is that when we point the telescopes down, Mexico City is about to show up. At some point you'll see the big one. We're basically just going down the Americas. I think it might be that. We really see that humans are extraordinarily concentrated in space. Something that was not true in the origin of our species, and that increasingly is true and is the norm around the world. So that's what's been happening in the last century, especially in the last decades in Asia and in Africa. In Latin America, most of this change happened in the 60s and 70s, depending where. But really, there's a sense in which, as you know very well, the cities of Latin America are still going through the transition of growth and becoming cities that work maybe a little bit better. But in being so, they are very exciting places where cities are forming in some sense. I won't say much about Mexico because actually there's not, to my knowledge, a lot of very good data about Mexico. There are some that we've studied about homicides and demographics. But part of what we do, as I'll show you as I go, is to study cities all over the world. So to compare cities that are rich, cities that are poor, cities that are developing, cities that are very old, including some actually here too. So the challenge, I think, that already came up in Dick's great introductory talk is really that when you look at complex systems and when you look at cities, everything's entangled. You know, the social part of the city, how we interact with each other, how we learn from each other, how we exchange money and other things with each other, is all entangled with where we live, how we move around, with the kind of transportation we have. So there's a sense in which that's often the nature of a complex system. You have to put your arms around it by including all these things before you can even start. And that's why it's so difficult. Most of the thought and research that has existed in cities tends to be about looking at city in space. You have a map, you can characterize, you know, how space is filled, or you can maybe look at the economics of cities by seeing how many people like you with PhDs exist in a city and hope that has something to do with how prosperous it is. Or it could be about crime. But there's a sense in which all these things are connected in this interacting space that cities create. And that's basically what I want to tell you about. So this is, you may not know who she is if you're not into cities, but she's maybe the most famous person in urbanism, Jane Jacobs. She lived in New York in West Village. That's where she lived. It's now very different. But basically she's one of the people that fought in New York to stop urban renewal, which meant at the time in the early 60s in New York, that the city was being interpreted as a system of flows, a system that was built to move cars around, and therefore the most important thing to do in New York City that was very congested in the 50s in the post-war was to create lots of highways. And they were going to put, if you know New York, you've been to the Village, you know it's a lovely place to walk around and used to be, you know, a very artistic and intellectual neighborhood and so forth. but they're going to put a highway through it. And it's also interesting in light of, social power and so forth, that it was a bunch of people like her that were able to stop that, but they had media contacts, they had people like you to a large extent. But in other parts of the city that were poorer, that didn't happen, and there's a highway there, like the Lower East Side. So anyway, but let's stick with the scientific point, which is how is it that you deal with all these integral things when we look at complex systems? So I already said it, but just to say it slightly more in detail. So when you look at a complex system, what's really interesting about them is that everything seems to be difficult from the point of view of doing, I don't know, simple physics. So when you look at a city, people are different, organizations are different. So that's what heterogeneity means there. And that's part of the point. If everyone were like you, there would be no point in interacting with them. You learn something, you exchange something. This is also true in other interesting complex systems, if you think about it. It's true to some extent in the brain, where different parts of the brain code for different things, and it's true in ecosystems. There's this issue of circular causality. You can say that a city is rich because it has good infrastructure, or perhaps it has good infrastructure because it's rich. Which one is it? Okay, I'm sure that's a problem that you discuss almost every day in Mexico City. Everything is interconnected, usually in networks. When you think of transportation, it's a network. When you think of society, it's a network. When you think of the economy is part of the social network of the city, perhaps with different agents. So there are these networks. They're not just simple local interactions. They're kind of heterogeneous ways of interacting that define how a city works and how many complex systems work. And there's a sense in which all this is not just a thing. It's something that's changing. It's a process. It's a system that's evolving. I hear a lot of echo. Do you hear echo, or do you hear okay? Okay, sorry. So it's probably I hear myself and then the... Okay, so there's this sense in which not only is the structure individually different, interconnected in complicated ways, but it's also changing. So how do you describe that? And there's a sense in which you can understand complex systems in general by looking, so I just want to make a general point before I go square into cities, in terms of this complicated but very interesting interaction between information, matter, and energy. So let me make that general point. I put some names there. It's very incomplete in terms of giving credit to people, but just to highlight a few ideas. So if we wanted to have a theory of complex systems, you have essentially to deal with these three fundamental quantities. There's a sense in which, particularly until the 20th century, we've learned to deal with those two quantities very well, matter and energy. And in fact, Einstein became famous, among many things, by showing how they're equivalent, and has this big factor of c squared multiplying m, and that means that there's a lot of energy per each bit of mass, and the rest, is history. But that means that the sun shines, and you can get nuclear energy and so forth. But we don't understand very well how matter and energy relates to information. So information is many things, right? It's information as in a book or in your brain, but it's also just the arrangement of things, right? That's how an information theorist thinks about it. It's the fact that things have particular places relative to each other. It's not just all a mess. So in what we do, in complex systems always have all this heterogeneous, complicated structure that's neither very simple nor not very random. So in physics, that's always what we do. In classical physics and traditional physics, what we do is either to assume that something is very simple, like a crystal, so the arrangements of atoms are very simple, or that it's very disordered, like a gas, where it doesn't really matter where things are, they just have some overall properties. But what's interesting is the place in the middle, where things have a structure in the middle that's neither too ordered or disordered. And there are many interesting ideas about how this is connected. We have now, in some sense, a theory of information unto itself in terms of information theory and computation. But I just want to highlight some of the arrows here on the left, on my left. So there's this idea that information is always physical. So if there is information, it is in things. It may be in your brain, maybe in a book, but more likely it's in the structure of a city. It's how it's organized or disorganized, right? And that's really important. It's not something that's ethereal. And so there's a cost in putting things in the arrangement of things. And that's very important. It's not that immaterial. The other thing that connects more to things I'll say towards the end of my talk, but it's a very interesting line of ideas that's still very under-formalized, it's not very well understood mathematically, is this idea that development, human development, how societies change, become richer, get to know more things, is really about information. It's about ability to acquire information, the ability to use that information to deal with the environment, hopefully in good ways, sometimes just in exploitative ways, but in any case. And it is how that information is embedded, again, in the structure of society, the physical information. So when we're able to do all that, to put those arrows together, we'll have a theory of complex systems. So think, if you're doing complex systems, you probably have to be doing a cycle of those three quantities. Okay, so now I'm going to get into cities. So I think the big revolution that we're going through in complex systems is not only that we've had interesting ideas for a long time, not only there have been concepts from many disciplines, Dick mentioned some of these, that connect in some interesting ways from economics to ecology to other social sciences to physics, but that now we have more data. So there's an opportunity. We don't have all the data in the world. There was a comment about that data is important. But I think now it's possible to start making better guesses, better theories, if you want, of what is going on. So that's the spirit of the rest of my talk. And so what we do is that we have this sort of slightly megalomaniac way of looking at the world, in which we look at all the cities in the world if we can. So we've had this almost 10-year program now of trying to get data for everywhere. So the color just means places. If it's redder, it means we have better data. And if it's gray, it means we have no data. And if it's in between, it's something in between. For Mexico, again, we have some crime data, we have some demographic data, we have some road data, but we don't have a lot of other socioeconomic quantities. And there's also an issue, I won't go into it in the talk, but how good is that data? For example, for homicides, there's big discrepancies between who collects it. But for all other countries, there are places like Africa and India where really urbanization is happening now. They're very interesting, on which we're putting a lot of effort. That's what the circles mean. And Latin America is interesting in that cities have formed now a generation ago, but they're still going through a big transformation in terms of their organization, their politics, their infrastructure. So here's what you find when you start looking at this data. Just the first few facts, which are already kind of, I find them absolutely fascinating. So when you look at cities of different sizes, so you pick cities, this statement doesn't quite make the point I'm making it more rigorously. So if you look in 2010, at all the cities in Mexico, and you ask, what's the GDP or the wages or the economic productivity more generally of Mexico City compared to a smaller city, you will find that per capita, typically the productivity of larger cities is larger and increases by a factor of 10 to 20% per capita. So it means that you make more money in Mexico City, you spend more money in Mexico City. Okay, but this is kind of interesting. How come does that happen? And this happens all over the world. The baseline is different. If you're in a poor country, you make less money than in a rich country, but the cities of that poor country make more money, the big cities of that poor country make more money per capita than the smaller ones. Here's another one that seems different, but it's actually, as I'll show you, the same thing, is that when you look at crime, and it's usually violent crime, it's crime of people on people, you find a very similar effect with very similar numbers, that per capita homicide rates or other violent crime rates also increase the larger the city. And this is why, in general, we have the perception that larger cities are also more dangerous. It's not clear this has always been so. If you read Steven Pinker's book, there's a sense in which once upon a time, a long time ago, the countryside was very dangerous and people would come to cities, think medieval times. But in modern cities for which we have good data, this seems to be almost always the trend. So what I'm going to show you now is a bunch of data that we analyzed, just to give you an impression of how this plays out. And I'll have to introduce a little bit of mathematics. I'll try to introduce always the idea. So if you don't like mathematics, just listen to the words. Hopefully they'll make some sense. But I want to show you that there is mathematics, because otherwise we would be back in Aristotle and Plato, who are already discussing how planned cities should be and so forth. So there's a sense in which it is really by formalizing ideas in terms of mathematical models that can be tested by data using a scientific method that we can make progress in complex systems. So what I'll do is something very similar. It's somewhat similar, but with very different quantities to what Manuel showed you about the variability of heart rates and time. But what you have here is basically a quantity like the GDP or wages of a city. So for example, the wages of New York or of Mexico City. The population of that city. Some exponent, which is like is alpha, I call it beta. But it's basically showing if this is linearly related. So if people made the same money per capita, this would be 1. It's not going to be 1, as I already showed you. And these are just fluctuations. And by showing you a plot, I'll show you how that works better. So here's an example. So this is the United States, cities of the United States. There are about 366 cities, about 50,000 people. The largest one over there is New York City, which is about the size of Mexico City. Mexico City may be slightly larger than New York, think about it, if you haven't already. So what you see here is that I did a trick. I removed population growth and I removed economic growth. So wages have increased over time, by and large, not every year, but most years, and population has too. But if you account for those two general effects across the country, you can put the lines, the points for 40 years in the same line, and here's what you find. They look all like they all fall on the same line, and that line doesn't have slope 1, it has the slope of 1.12 or 11 in this case. So it's this 11%, 15%. It's the number I've been referring to. And here's an example using, I think, 10 countries in 4 continents, I think, from China and Japan to Portugal and Spain to Turkey and Brazil. We got nice to have Mexico, but again, Brazil actually has very nice data. It's a large country, so we use Brazil a lot. And here you find a similar effect. So this is not wages, GDP. And this is just expressing this 14% increase. I like to call this, in some sense, the urban economic miracle. So one of the reasons why, at least an economist will tell you we're having urbanization, the purely economic effect is this, is that GDPs, wages, incomes, economic profits in companies, all tend to go up on the average. Now this average hides a lot of things, but on the average goes up the larger the city. So by creating larger cities, these positive effects are just sort of magnified. And it's a universal effect. And here's just 4 different quantities, just to show you that this is not just about money. Quite the contrary, as I'll show you, it's a social effect. It's not an economic effect primarily. But wages, crime, patents, which are sort of a measure of technological innovation, so new ideas being created, and GDP for the United States all have, again, this effect. They all grow faster with city size than linearly, so they grow per capita. So this is sort of the puzzle. How do you explain this? What's going on? What are cities doing? Are cities like other things that we know in nature? What is the dynamics that they're realizing? And can we understand it? So here's just one more plot about these, and then I'll start showing you the arguments with a little bit of math, and then I'll show you just pictures of what that means. So here's something I haven't shown you yet. This one is the same. It's GDP of American Cities, so I showed you that already. But this one is roads. So it's basically the area of roads, not just the length, the area of roads. So if you have lots of highways, you have to account for the width in cities in the United States. And so what you find is that this effect is that you have less, so this is the line of the same road per capita, and this line that's below that one is showing that you have less road per capita the larger the city. Something very familiar to you in Mexico City, I'm sure. At least familiar to me after 2 days of going around the city in cabs. So there are these 2 things that are weird, right? So the city is becoming, in some sense, in this sense of looking at infrastructure, there are more people, more cars per unit per area of road, so it's denser, and these socioeconomic outputs tend to be increasing. And the effect is more or less that they go with 2 different exponents, but this has the same deviation across the simple effect of cities just being made of people without interaction. So I wrote a paper explaining this, fortunately just a few months ago, so I have an answer for you, otherwise I'd be giving this talk very differently. But these are cities in China, just forming, so it's sort of interesting. But what the theory says is something, let me just show you a couple pictures before I go into the more formal argument. So what is a city? So there was a talk before, I think it was in Dick's talk, about this problem of different time scales or spatial scales. That when sometimes you have things that move very quickly and other things are slower. So you can think of the slower ones as some background, like this room is going to be here for a long time, whereas we'll come and go. But so what you see here is a train station, the main train station in Mumbai, and what you're seeing is the trains and the infrastructure. Generally, it's just there, it's sort of slow, but you see this flow of people just through. So in some sense, the fast dynamics of a city is really the people. People moving around, people doing what they do. And then there's this background of infrastructure that in general is slower, but of course also evolves on timescales of maybe decades or a few years. And so how do you capture this interaction between the people and their interactions, which is a social network, and sort of the background built space that we build in order to facilitate that. Okay, this is a very old problem in planning. It's actually attributed to Kevin Lynch at MIT. If you know about urbanism, you've heard about him. He's a very interesting character, and he'll come back in a later slide in a very different guise. So I had to show you this after being in Mexico City for a couple of times. You think you have bad traffic, but this is Ho Chi Minh City in Vietnam. And this is a little bit besides the point, but self-organization of traffic. Look at that. Anyway, a city is not really that planned. It's not a crystal, right? It's this thing that's moving. People are moving around doing their thing. It's again speaking to the fact that there's the road, but the way people use these spaces is just incredible, right? And you know that. And there's a sense in which by people doing their thing sort of individually or in small groups and self-organizing, you have a city that works. It may not work very well, but it's already sort of working. And so that's where we need to start, is to start to think about a city as a social network, okay? So that's kind of important because most people think or thought for a long time of cities as built spaces, as the infrastructure, as the trains, as the roads. And that's what mayors tend to do. But in fact, I mean, that's all just to help. What you need to start with is people. And why is it, what kind of social structures do cities promote? What kind of structures do they create? Now, there's a long answer to that, and much of it we don't know. But what I'll just show you is some of the general characteristics of these social networks that make it be and give the effects that I was talking about before. Okay, so the idea here is basically, see, you can tell I'm not a graphic designer, but here's you, and you basically have a trajectory in the city, this little red line, you go here and there, obviously an American city. Or Roman city, I guess, but there you go. And as you go around the city, you interact with people all around it. And so basically you are this path in space. You are a collection of interactions that's embedded into another network, which is space itself, but it's not just space. It's space that we created in order to promote movement. So that's sort of the entanglement that we're trying to get our arms around and explain. Okay, so now there's a map. But let me just tell you the ideas again. So the first idea is that if you think about that in a somewhat idealized way, you can borrow a little bit from ecology or from epidemiology and think that what we're trying to create in this room, I think, hopefully if it works, is that we could all talk to each other in principle. We won't do that. If each one of us had to talk to each one of us, it would take a long time. It would go like n squared and so forth, you know, if you can do the math. But this meeting is created, I think, and the organizers can correct me, with the intention that we could talk to each other. And the city, in some sense, is trying to create that dynamics over a very large scale. It's creating a space in which you can move around, and in principle, I know you look at Mexico City, it doesn't look like that necessarily, but in principle, you could meet with anyone there and do the exchanges of information, of fun, of whatever you do that would be interesting. And so what that means is that space itself is, so if we're in a city to interact with each other, to get that advantage, when that's an advantage, then space must be constrained. It's like a rocket problem that basically you're stuck to the Earth because there's a gravity field. Here we're stuck to cities. You live in Mexico City because there are lots of things in Mexico City that you need in your life. And that is an effective, it's not gravity, but it's an effective attractive force. And that means that space gets constrained by that attractive force. And that means in particular that the area, the overall area of the city, once you put in the costs of moving around and the benefits of interacting with other people, will have this character. I'll show you more about it later, but that goes like the population to some exponent, which in the simplest case is about 2/3. And it turns out that some of you came from Europe, your ancestors, many of you lived here before. People who lived in the Valley of Mexico before Columbus actually knew that already. They were building cities in that way. And I'll show you a little bit about that. We just finished the paper on it, so I'm excited. The other thing is that these infrastructure networks, the roads, the railways, the pipes, they basically need to grow as you go. And this has been discovered already in the United States in people looking at transportation. But sort of the idea, the way we seem to do it is that we look at the density of the city around us as we stake another bit of ground. We could be a constructor, maybe somebody building their own shelter. And we try to put it sort of in the middle so that you're close to most people, but consistent with the density that you encounter. It's a little bit like if you go to the beach, and you don't need to do this, but often people put the umbrella sort of as far away from other people, but sort of in the middle of other people. So you're not far, not too close, not too far from other people. So basically that's how we build infrastructure. So as the city grows physically, there's a little bit of infrastructure that's added, but it's added in a sort of a self-consistent way with the density of the city already. And that allows you to, instead of having networks that are planned from the beginning, that cannot change, it allows these networks to be decentralized and evolve. So they can be added piece by piece. And that's really important. It's very different from biology, from your vascular system, for example, which is an analogy we had started with. The other issue is that, and I know you look at Mexico City, it doesn't sound that way, but there's a sense in which when you live in a large city, you cannot have 10 times the effort in your life and the travel, at least adjusted for means of transportation, that you would have in a smaller city. There's a sense in which your human time and cognitive abilities are limited, and so you have to have a way of dealing with living in a larger city without that pushing you to a regime where, so in some sense the city needs to evolve around you, and you need to adapt to the city, but that adaptation has to be within bounds, so it's not a power law. That's the point. And finally, that social outputs are essentially proportional to the number of interactions that people can have, at least on, and I'll come back to this. This is a little simple when you start looking at poor parts of cities and rich parts of cities and other things. But so I'll go now a little faster because I already introduced these ideas. But this allows you to start basically thinking of space in the city in terms of this balance between moving around and interacting. And this gives you this first sort of law. And then you can actually derive something that economists have been trying to derive for a long time, but from a social network, the way a sociologist would actually hopefully be proud of. So there's a sense in which you start with a graph, with the social network. We'll hear more about social networks as we go through. This is just the math, and then you say, if your interactions are local, so that I interact with somebody, I'm interacting with you now in some sense, but if you're going to have a good conversation, we'll have to go to a corner and talk a little bit more. So in that sense, a lot of what happens that matters in the city is also of that sort. And then you can go through some math and you find that formula that I was showing you before. Sort of this city as interaction space. And then more math, it's almost through, but is that you actually look at this infrastructure, and it's kind of curious. Have you ever thought of why don't we just have roads of the same width? Why do we have highways and middle-sized roads and low paths and corridors in a house? You know, so just think of how that works, right? And what are the highways for? Well, in some sense, they're to move around across the city, and then you have things in between. But one thing that's very interesting is that try flying at night over a city, if you're leaving the conference, or next time you're on an airplane. If it's at night, look down. If it's during the day, you can do this too, but it's hotter. Look down and see how many cars are there in the large roads, like the highways, and how many cars are there in the little roads. And you will find, I think, but email me if you don't find this, that you'll find many more cars in the highways. The highways are bigger, they're wider, but they have a lot more traffic in them. And this is very important, you'll see. This is why you're always stuck in traffic, usually in the highway, or in an intersection of two main roads or something. Okay, but you can go through this and see basically what is the geometry of these networks, and then try to actually do the calculation of what's the cost of moving around. Okay, this is telling you that in Japan this works, and this is human-bounded effort, so I'll move through this. But there's a lot of very cool, it's simple mathematics, just bringing lots of things together. But it's basically you can use, you know, physics of circuits to get this. And basically what you find, there was a question about criticality in complex systems, and so here's the answer for cities. The answer is that cities are critical, and this is because the costs of moving around are actually very commensurate. They are commensurate in cities that work with the benefits of interacting in the city. So after all that math, what you discover is that the interactions have this character. They go like n to the 1 plus 1/6, 7/6. But the costs go just the same way. They're not the same. The constant in front is different, but they're a fixed percentage. So you can't really get ahead. You just basically, you build a bigger city, you feel all this congestion, all this happening, but you're also still there. And why are you still there? Because you're interacting with people that you like better than in a smaller city, and with businesses and so forth. So there's a sense in which this is why you don't just have large cities, or you don't just have small cities. We have cities of all sizes, because these effects kind of cancel all across size. Okay, and there are two ways by doing a little bit more manipulation, just a little bit, just to put icing on the cake, so to speak. You can discover that you can change this interaction strength, the quality of interactions in the city, which is something that, you know, it could be crime, it could be money, it could be, you know, people are your friends, or your partners, but this G basically measures a little bit of that, the quality of that. And because the costs and benefits actually are not the same on that parameter, it means that you can have these two ways in which a city either exists in the first place or ceases to be. Or you could just have sort of the American Florida exurban demise, where you basically have cities that are so spread out, they have to travel so far to get anywhere and interact with people that that's no longer really a city. So there's a sense in which by having too much infrastructure, in this case, or too little per person, you end up with very different cities that are just on the verge of existing. My knowledge, Mexico City does a little bit of both, in some sense. So this is, I just want to now move a little bit more quickly through things. I just want to point out, so these are many things you can predict, but one that's interesting is this, land value, okay? Land is very interesting because it compounds these two effects I've been talking about. The fact that the city is getting a little bit denser in space, but also that we have more money per capita, okay? So if you put these two things together and ask, well, what is the value of land? So this is basically less land per person and more money per person. Deposit that money on that land and you get land that rises. The value of land rises faster than incomes, much faster. So this is the reason why lots of things happen to large cities, and I'll show you pictures about that in a second. But you know, the city goes 3D a little bit, you build and you go underground. Why it's very expensive to keep a car around, because it's this thing that's large, and if you want to have a car in Manhattan, you probably cannot have a room in your house, so do you want a kid or do you want a car, you know, that sort of thing. So, and this is basically showing the effect of interactions. So I'm showing you now some data. This is data from my native Portugal, and its interactions measured using cell phone data, and this starts getting us, with all the problems of cell phone data, at how these interactions actually are realized in cities, but they agree with what the theory predicts, and also gives a little bit more because we can do the statistics, and we're working on that, and I'll tell you more later. And this is just, I had to put this in, it's a new paper, it's still a working paper, but with some colleagues who are archaeologists and study the basin of Mexico. You might recognize it there. This is before, of course, the lake disappeared, and this is the extent of Mexico City in 1960. But basically, this is the formative period. If you care about all the history of archaeology and the Valley of Mexico, it's the Aztec period. You see a lot more cities here. But basically, these people already were building cities that spatially, we don't have a lot of good socioeconomic indicators, that spatially have essentially these signatures that I was describing to you. So we're very excited when we saw this, because this is a system of cities where these people didn't know anything about cities in the old world. You know, it was an American invention, the way it was invented, but still it's the same. So there's a sense in which the city is a general sort of invention, a process that every society tends to benefit and develop towards in some cases. So let me just show you some analogies. So one of the things we started from, because of the work that Jeff West had done, was to compare, and many people have done this in different ways, compare the way cities look like to organisms. A lot of urbanists do this anyway. And I mean, there's an obvious difference why cities are not like organisms. We, unfortunately, that was the Manuel's talk, we have to die, right, in order for things to evolve. Tough, but you know, that's biology. But cities don't do that, right? A city as a whole, of course, people come and go, people die and live, but also they migrate. But there's a sense in which cities evolve and change their infrastructure, just as I was describing, in a way that does not require the city to disappear and be reinvented again. So cities need to adapt and evolve. And so, yes, this could look a little bit like the structure of neighborhoods, but when you look at the numbers for the highways, so to speak, and the middle roads and so forth, this is wrong, actually, as it turns out. So it's close because it fills space, but it's not the same. And the difference is functional, is because one evolves and the other one is built once and for all. So here's another thing. You might also have your parallel in Mexico City, but this is Delhi in India. And when large cities, you just have this weird stuff that's kind of ugly, right? Where infrastructure just is in your face. It just occupies lots of space. So there are cables, there are roads, and that's all you see. Why is that? And the reason is because all this infrastructure, as I showed you before, grows faster than space itself. So in larger and larger cities, the fraction of land that's occupied by infrastructure is larger. And so you just see it everywhere before it disappears. And it disappears underground and overground, right? So this is New York. There was a big ice, this is in 1890s. There was a big ice storm. You're free from that here, I think. So all the cables came to the ground, and finally they decided to bury them. And you go 3D as well. This is Hong Kong, right? So this is kind of extreme. There are these photos of Hong Kong, if you're interested in this, just mind-boggling. Or you go underground, right? And you know about all this in Mexico City. So the other thing that has to do with the structure of more cars in highways is that most of the dissipation and the costs actually are happening in the large roads, in the large pipes. And so this has interesting consequences. There are some geographers and economists that try to quantify this without much theory, but there's a sense in which it's the highways that always clog up. And this is the record, to the best of my knowledge, of the biggest traffic jam in the world. It was in China, as you might expect. But São Paulo, I don't know about Mexico City, are up there as well. They had a huge traffic jam in the new highways of China. In some sense, they're just building them. They're not thinking about what they're doing. So there's a sense in which it's these large, there's links across cities that tend to jam up. And so this is basically the way the city looks like and how the traffic flows go. But there's a sense in which I want to leave you with, that there's something that functionally, in the way that it works, looks a little bit more like a city. And this one is for you nuclear physicists, which is this, right? That's the sun. I don't have to tell you. But what is the sun? The sun is a nuclear reactor. It's a place where a lot of mass come together, interacts at the center. You have nuclear reactions that create nuclear chemistry. They release light and neutrinos and other things, and that create new elements in large enough stars. And what you find is that, therefore, the sun is a nuclear reactor, but it has the very interesting properties that the more mass a star has, the more light it emits per unit of mass. So these reactions are getting faster. Everything's getting faster, and this is because it's an attractive, a system set by attractive interactions in chemistry. And there's a sense that cities are much more complicated than this. They're much more two-dimensional, but they have some of the same elemental dynamics of being an attractor for social interactions. So that's what a city essentially is. It's a general purpose social reactor. It's a place for us to come and do whatever we do socially, and we keep inventing what it is that we do socially. Sometimes it's good, most of the time it's good, sometimes it's bad, but that's essentially what a city is. So in my last 1 minute or minus 2 minutes, let me just tell you a little bit more inside the city. So far I talked about the city as a whole. But one of the things that's kind of important and maybe curious scientifically is how different cities are inside, how different people are, how different neighborhoods are, and so forth. So this is more work in progress. There are a couple of working papers, but let me just show you that because I'm excited about it. So these are just professions in the United States. And I don't know in Mexico, but the most common profession in the United States it's now services. So it's shop assistant, cashier, it's shops. So you look at different cities, they have different amounts. In New York, there are almost 1 million shop assistants and so forth. But these all are the same. So cities in some sense realize the same abundance of these functions. But they do so in a way that gets deeper and deeper the larger the city. And so you basically have a way in which larger cities have funky professions because they go deeper in this distribution. And you can understand this in terms of a differentiation process. When you come to a city, you can become a very good complex system scientist because other people do other things for you, hopefully. Is that the way it works here? So if that works, you actually can specialize, can coordinate with others that do other things, and can learn. And it's in the learning, in the generation of the information, that cities really produce an advantage and produce change in human societies. Is that to the extent that the information has material and energetic consequences, societies will change. Okay? That's a story that is much longer than I can tell you now, but there's a mathematics to this that's also simple and quite beautiful that we're starting to get. So finally, I just want to end with something that is more work in progress, but I think is very interesting, which is this issue of development as information, and where is that information in a city? So there have been these very interesting ideas. This is a book about São Paulo, and it's an anthropology book. But he makes some of these arguments in quite a beautiful way and tells the story of how São Paulo is developed as a civic city, as a lot of the favelas have been integrated, the ones that have, and have become part of the official city with citizens with rights and obligations, and how this process actually occurs. So it's the story of that process. And the story is basically a process of a network forming. If you are a mathematician. It's a network in which you come and you settle on the side of the city and you're not integrated, you just try to survive. And then slowly you start finding maybe a job or a way of finding information or a partner or a friend. and you become integrated in the social network that the city is. So there's a sense in which by doing that, by improving your life, you're also in some sense changing the city. And we know, of course, Lula sort of grew up in a favela, and President of Turkey did too, and that's the natural way in which things have changed in countries that have gone through this cycle. But we looked at this increasing, I just want to say that actually the foundational study that changed international policy for many decades was done in Mexico City. And this is very obscure, very. It's a thesis from a PhD in 1976 by a Polish man called Tomasz Suter. And he basically went all around Mexico City in the 70s and measured all kinds of socioeconomic characteristics and how those changed with the sort of socioeconomic integration. And this made sort of the structure of planning for poor neighborhoods in terms of just relocation from the top down start to be basically processes of infrastructure upgrading and so forth. This is a long story too, but if you're interested, it's very interesting. And sort of my personal mission being in Mexico City is to understand to what extent these ideas influenced Mexico or just went somewhere else, maybe internationally, and did not change Mexico. So there's a very interesting story there, but there's also a process. And Kevin Lynch was one of his advisors, and the other advisor is John Turner, who was an anarchist writer. And this was one of the rare times when an anarchist writer, inspired by what was happening in a developing country at the time, changed completely and inspired and rewrote the policies of the World Bank. So it's sort of a very interesting story. And I know I'm over time, but just wanted to tell you that. So we've done some of these network analysis and network change using now cell phone data and other things. This is Cote d'Ivoire, showing that cities actually are more integrated than we think, but basically what happens is that there's a lot of informality. So the temporal uncertainty dimension of how these networks form is still something important to study. So we have now a lot of data studying the formation of neighborhoods, particularly informal neighborhoods, especially in Africa and in Asia. This is Sao Paulo. But there's a sense in which cities actually, in some sense, are more normal to start this way. This is kind of extreme, and it's a beautiful photo, but you know what I mean, certainly. But there's a sense in which they also order, in the sense of forming these networks of infrastructure and opening up the city so that the city is not just a local neighborhood, but it's an open social system. So that's what we're studying essentially by using this data, is to characterize the process at the individual and neighborhood level of the characteristics of individuals and neighborhoods in a vast city and how that process changes as a way of getting to the process of development. And it's very interesting because what we find, this data is exceptional because we have information about individuals, which you don't get from census data. But what you find is that there's information in individuals and neighborhoods that reflects this dynamics across the city. It's of course true sometimes that in a very poor neighborhood you're reflecting sort of a biased sample, if you want, a poorer sample of the city as a whole. But you see the signature of these interactions in the statistical distributions that we see. I won't show you the math, but it shows you that the city, again, is a place where you interact socially and where these interactions are changing over time. And so I think there's a lot of promise to create sort of a theory that's sort of a statistical physicsy theory of how people interact and how this conditions space, how they co-evolve, and how cities form. Good. So this is my last slide. And I just want to come back to these final and initial themes and basically say something about complex systems more generally, not just cities. Is that in some sense, it's by putting all these ingredients together, and you better do it in some sense, you have to do them in a rough way, not in a way that's particularly detailed about each part of the system. But in putting these ingredients together, you really have a chance of starting to create knowledge about not only perhaps how complex systems are, but how they evolve over time. And to, in some sense, enrich some of the ideas that we have from biological evolution and from physics that in some sense try to bring this together, but to understand in a new realm, using new data, using new ideas that will really allow us to create something new. That's the end of my talk. I just had one slide that's very different and addresses one question, which was, there was a question before about what makes good interdisciplinary scientists or institutions. And this is from Oliver Williamson. He is from his Nobel lecture. He's an economist, but his early education was at Carnegie Mellon, and so there's a C3 there. And that's why I went to fish it. That kind of rang a bell. And he, in his words, I know I'm taking too much time, but be disciplined, meaning be grounded on something. You have to. So this is describing Herbert Simon and all the incredible work on economics and artificial intelligence that came from that group. be disciplined in that you have to know something and take your discipline seriously. Be interdisciplinary in that if your problem requires knowledge from other disciplines, go get it, go talk to people. But have an active mind. If you do that, for sure, you will encounter problems that have not been solved, that you have to ask new questions. Don't just take lore for what it is, but ask new questions. Thank you.